Hi students, welcome to Home School. In this session, we are going to discuss the sample paper issued by the CBSE board for class 12 examination 2022-23. Let's see the instructions given by the board. See, then there are 35 questions in all. All questions are compulsory. This question paper has 5 sessions. Section A, which carries 1 mark. Then there are multiple choice questions are there, and assertion reason type question also be there. Okay, then section B, the 2 mark questions. Then section C, it carries 3 marks. Section D, 5 marks. And finally, section E, okay, that is case study. So that questions carries 4 marks. Okay, then there is no overall choice. However, an internal choice has been provided in section B, C, D, and E. Then you have to attempt only one of the choices in such questions. Then use of calculators are not allowed. Okay, so let's go for the first question. According to Coulomb's law, which is the correct relation for the following figure? Okay, so the figure is given. Then there are 2 charges, Q1 and Q2, separated by a particular distance. And here 2 forces are given. One is vector F12. Then this force denotes the force on charge 1 due to 2, okay, that act along Q2. And the next force is F21, okay, that is the force on charge 2 due to 1, okay, that acts in the direction of Q1. That means these 2 forces act in opposite direction. That shows the attractive in nature. So we have to predict that magnitude, that is the sign of the charge, as Q1 as positive and Q2 as negative. Okay, so these 2 are unlike charges. So how can we represent the unlike charges mathematically? So let's go for the options, that is Q1, Q2 greater than 0, Q1, Q2 less than 0, Q1 equal to Q2 equal to 0, and the fourth option, 1 greater than Q1 by Q2 greater than 0. So here the option second is the correct one. Okay, that is Q1, Q2 less than 0. Okay, this is the representation of unlike charges. Okay, so second question. The electric potential on the axis of an electric dipole at a distance r from its center V. Then the potential at the same distance on its equatorial line will be. Okay, so here we have to find out the potential at a point at the same distance on the equatorial line. Okay, that we already learned in the theory classes, right? Then that is, if we draw a dipole, okay, this is minus Q and this one is plus Q. Okay, then we consider center O here. Okay, that is the midpoint of the dipole. Okay, then if we draw a perpendicular line, this will act as a equatorial line, right? Okay, so we consider this distance as R. Now we have to calculate the potential at point. Let us consider the point P. Okay, so at point P, then due to this dipole, the potential V equal to 0. Okay, that we already learned in your theory classes, right? Okay, so here the option 4 is the right answer. Okay, then we are moving on to the next question, question 3. That is, the temperature T, dependence of resistivity of materials A and B, is represented by the figure 1 and figure 2 respectively. Identify the material A and material B. Okay, then here the figure is given. Okay, in figure 1, it is clear that when the temperature increases, the resistivity decreases, right? Okay, then in figure 2, when the temperature increases, the resistivity increases. Okay, so in figure 1, okay, here the temperature increases, but the resistivity decreases. Okay, in which material it happens? Okay, that is for figure 1, it is a semiconductor. Okay, that is the graph 1 corresponds to the semiconductor material. Okay, then figure 2, there is increase in temperature. Then according to that, the resistivity also increases, right? So that is a conductor. Okay, so let's look at the options. Material A is a copper. So first option, we have to neglect that one because material A, okay, that is, it is not a conductor, okay, because we from the graph itself, we concluded that that one is a semiconductor. So we have to neglect the first option. Then second option, material A is germanium. Okay, germanium is a semiconductor, right? Okay, so that this one germanium, and material B is copper. Copper is a conductor. Okay, so we have to take the option 2 as the correct answer. Okay, then we are moving on to the fourth question. Two concentric and coplanar circular loops P and Q have the radii in the ratio 2:3. Loop Q carries a current 9 ampere in the anticlockwise direction for the magnetic field to be 0 at the common center. Loop P must carry. Okay, here we have two loops. Okay, that is, one is Q, okay, which carries a current of 9 ampere. Okay, then and have radius. There is a radius is given. Okay, then radii in the ratio 2:3, right? Okay, so Q having the radii, I took this one as 3R. Okay, you have to take 3 also. Okay, then the another loop. Okay, the another loop is P another loop P having radius 2R. Okay, this loop is considered as P. Okay, then for the magnetic field to be 0 at the common center, here we consider the common center as O. Okay, so if the magnetic field at the center O is 0, that means in P, the direction of current should be in clockwise direction, because the direction of current in the outer loop, that is Q, is in the anti-clockwise direction. So that we have to take the direction of current in the loop P in clockwise direction. Then only the magnetic field at the center O will be 0. Okay, so that we have to calculate. Okay, then direction is given, but we have to calculate the current in the loop P. Okay, for that we are going to play, that is magnetic field due to Q is given by mu 0 I by 2R. Okay, mu 0 I by 2R, that is 2 into 3R. Okay, then I due to Q. Okay, then at P, okay, for the loop P, we had to write BP equal to mu 0 IP by 2 into, then that is 2R. Okay, then we have to equate these two, we get BQ equal to BP. Therefore, mu 0 IQ divided by 6R is equal to mu 0 IP divided by 4R. Okay, here IQ is 9 ampere, so we have to write it as 9. So here mu 0 get cancelled, R and R get cancelled. Okay, therefore, from this IP equal to 9 into 4 by 6. Okay, 9 into 4 by 6. Okay, therefore, this is 3, 2, then 3, sir, 3, that is 3 into 2, that is 6 ampere. So, the current in the loop P is 6 ampere. So, the direction we already find out, that is clockwise direction. So go for the options. First one, 3 ampere in clockwise direction. That's wrong. 9 ampere in clockwise direction. That's also wrong. 6 ampere in anti-clockwise direction. That's also wrong. Then the last option, 6 ampere in the clockwise direction. So this is the correct option. Okay, option 4 is the correct one. Okay, clear. So we are moving on to the next one. That is question number 5. A long straight wire of circular cross-section of radius A carries a steady current I. The current is uniformly distributed across its cross-section. The ratio of the magnitude of the magnetic field at a point distant A by 2 above the surface of the wire to that at the point distance A by 2 below its surface is. Okay, here we consider a straight conductor. Okay, a long straight conductor. Okay, having radii A. Okay, then we have to find out the ratio of the magnetic fields. Okay, then A by 2 outside. Okay, A by 2 distance outside. We consider this point as A. Okay, then now we have to find out the magnetic field at point A. Okay, for that we are using the equation that is B outside is equal to, write the expression for the magnetic field due to a straight conductor, that is mu 0 I by 2 pi r. This is the equation. Okay, for a straight conductor it is 2 pi r. Okay, so here the current is I. It's okay. Then what about the distance r? Okay, here the point A lies from the center having the distance A plus A by 2. Okay, so that we have to write it as A plus A by 2. Okay, that is equal to mu 0 I by 2 pi 3a by 2. So 2 and 2 get cancelled. We get mu 0 I by 3 pi a. Here it is B out is equal to, outside it is mu 0 I by 3 pi a. Okay, then next one is in interior. Okay, inside. Okay, inside we have to take the distances. This one is point B. Okay, then this is A by 2. Okay, then for that we are using the equation for outside, that is B, sorry, not outside, it is inside. B inside is equal to mu 0 I, okay, then R inside divided by 2 pi the radius of the circular loop, radius of the conductor. Okay, therefore that is equal to mu 0 I into R in. What is R in here? That is A by 2. So we have to write it as A by 2 by 2 pi A itself. Okay, that is equal to A and A get cancelled. We get B in is equal to mu 0 I by 4 pi. Okay, 4 pi by, here is a square term also. Okay, so there is a square term, that is B in equal to mu 0 I R in by 2 pi A square. Okay, therefore we get mu 0 I A by 2 divided by 2 pi A square. Instead of A square we have to, okay, one square will be cancelled. Okay, therefore we get 4 pi A. Okay, now okay, we have to find out the ratio, that is the ratio between the ratio of the magnitude of magnetic field at the point distance A by 2 above. That means B out by B in. That is equal to B out. What is B out here? Mu 0 I by 3 pi A into 4 pi A by mu 0 I. So mu 0 I get cancelled. Okay, then pi A get cancelled. We get 4 by 3. So ratio is 4:3. Okay, so here the third option is the correct answer. Clear? Okay, now we are moving on to the next question. That is the sixth one. Here, if the magnetizing field on a ferromagnetic material is increased, its permeability, okay, then we have to write the expression for permeability, mu equal to B by H. This is the expression for the magnetic permeability. Okay, mu equal to B by H. Here, H is the magnetizing field. Okay, then carefully read the question. If the magnetizing field on the ferromagnetic material is increased, that means if H is increased, what happens to mu? Mu will be decreased, right? Okay, so here the first option is the correct one. Clear? Okay. So we are moving on to the next question, question number 7. That is, an iron cord coil is connected in series with an electric bulb with an AC source as shown in the figure. When iron piece is taken out of the coil, the brightness of the bulb will be. Okay, so carefully listen. That is, we are considering an iron rod here. Okay, then if we pull it out, okay, what happens? Okay, then what happened is that the L, that is inductance, will be decreased. Okay, so that the inductive reactance XL, that is XL is given by XL is equal to omega L. Okay, then if L is decreased, what happens to XL? XL is also decreasing. That means the resistance of this coil, okay, will be decreased. If the resistance decrease, the current will increase, so that that bulb will glow brighter. Okay, so here we have to find out what the brightness of the bulb will. Okay, what happens to the brightness? It will increase. So option 2 is the correct answer. Clear? Okay, now the 8th question. Which of the following statement is not true about the properties of the electromagnetic waves? Carefully read this question. Not true. Okay, that's the point. Not true. Okay, so the 4 options are given. Okay, the first option, these waves do not require any material medium for their propagation. That's the correct one. Okay, then second one, both electric and magnetic field vectors attain the maxima and minima at the same time. That's also correct. Okay, then third one, the energy in the electromagnetic wave is divided equally between electric and the magnetic field. That's also correct. Then the fourth one, both electric and magnetic field vectors are parallel to each other. Okay, so here this term, that's wrong, because we already learned that electric and magnetic field are in perpendicular. Okay, electric and magnetic field are in perpendicular. So they makes an angle 90 degree with each other. Okay, so the fourth option is not true. Clear? Okay, then the 9th question. A rectangular, a square, a circular and an elliptical loop, all in the XY plane, are moving out of a uniform magnetic field with a constant velocity vector v equal to vi. The magnetic field is directed along the negative z direction. The induced EMF during the passage of these loops out of the field region will not remain constant for. Okay, out of these 4, okay, which one have the EMF, okay, is not constant? So let us consider the magnetic field which is into the bottom. Okay, which is into the bottom. Now we are going to consider a rectangle, a square, then a circle and an ellipse. Okay. Okay, and an ellipse. Okay. So these 4 loops are moving out of this magnetic field with a constant velocity. Okay, these loops are moving out of the field with a constant velocity vector v. Okay. Okay, then our question is, during the passage of these loops out of the field region will not remain constant. That is, the induced EMF will not remain constant. We have to find out that. Okay, then carefully look at this structure of these 4 loops. Okay, then from these structures, then these 2 loops, okay, that is the rectangle and the square, okay, having the same, okay, same shape, right? Okay, so if they move out of the field, okay, the EMF will be constant. Then what about the circle and ellipse? The area is different, right? In the case of rectangle and a square, the area, okay, per time is constant, right? But here, circle and ellipse, okay, what happens when it move out of this magnetic field? The area will be change. Okay, there is a change in area. Okay, so that there is no constant EMF in the case of circle and ellipse. Okay, so go for the options. The first option, any of the 4 loops? No. The circular and elliptical loops. So this option is the correct one. Okay, circular and elliptical loop. Clear? Okay. Then 10th question. In a Young's double slit experiment, the path difference at a given point on the screen between the 2 interfering waves is 1/8 of the wavelength. So path difference, that is delta, is given. Okay, delta is equal to 1/8 of the wavelength. Okay, then the ratio of intensity at the point to the center of the bright fringe is close to. Okay, so we have to find out what I by I0. We have to find out I by I0. Okay, for that we have to first write, we have to find out the phase difference. Okay, we have the equation for phase difference, phi equal to 2 pi by lambda into delta. That is equal to 2 pi by lambda into the delta is given, that is 1/8 of the wavelength, therefore lambda by 8. So lambda get cancelled, 2 and 8 get cancelled, we get 4, that is phi equal to pi by 4. Okay, pi by 4. Now we have to write the equation for intensity, that is I equal to I0 cos square phi by 2. This is the expression for intensity. Okay, therefore I by I0, okay, this one we have to find out, right? I by I0 is equal to cos square into, what is phi here? Pi by 4. Okay, therefore pi by 4 divided by 2, that is equal to cos square pi by 8. Okay, while calculating this, we get the value as 0.85. Okay, so the option 4 is the correct answer. Okay, clear? Okay, now 11th question. The work function for a metal surface is 4.1 electron volt. The threshold wavelength for this metal surface is. Here we have to find out the threshold wavelength. Okay, so for that, the work function, that is phi 0 is equal to 4.14 electron volt. We have to convert this electron volt into joules, that is 4.14 into 1.6 into 10 raised to minus 19 joule. Okay, this is the work function. But work function we have to write in terms of lambda, that is hc by lambda, that is equal to 4.14 into 1.6 into 10 raised to minus 19. Okay, here we have to find out what lambda, therefore lambda equal to h. What is the value of h here? That is 6.624 into 10 raised to minus 34 into c, that is 3 into 10 raised to 8 divided by, okay, then 4.14 into 1.6 into 10 raised to minus 19. Okay, now we are going to calculate this. That is equal to, when we calculate 4.14 into 1.6, we get 6.624. Okay, now we have to cancel this one. Okay, therefore we get 3 into, okay, 10 raised to minus 26 into 10 raised to 19. That is equal to 3 into 10 raised to minus 7. That is equal to 3000 into 10 raised to minus 10. That equal to 3000 angstrom. Okay, so let us go for the options. See, first option 4125 angstrom, second option 2062.5 angstrom, and the third option 3000 angstrom. So we get the answer as 3000 angstrom. So the third option is the correct one. Clear? Okay, so our 12th question. The radius of the innermost electron orbit of a hydrogen atom is 5.3 into 10 raised to minus 11 meter. The radius of the n equal to 3 orbit is, okay, we know that the radius r is directly proportional to n square, isn't it? Okay, so that for the innermost orbit, that is r1, okay, is equal to, we have to write it as n1. Okay, that is, it is proportional to n1 square, isn't it? Then likewise for the third, right, the radius of n equal to 3 orbit, that means we have to find out r3 is directly proportional to n3 square, right? Okay, so we have to take the ratio, that is r1 by r3 equal to n1 square by n3 square. That is r1 is given. What is r1 here? That is 5.3 into 10 raised to minus 11 by r3 is equal to 1 square by 3 square. Okay, therefore r3 is equal to 3 square is 9. 9 into 5.3 into 10 raised to minus 11, isn't it? Okay, that is equal to, okay, 5.3 into 9, that is 5.3 into 9, 7, the remainder 247, right? Therefore 47.7 into 10 raised to minus 11, that is equal to 4.77 into 10 raised to minus 10 meter. Okay, so let's go for the option. See, the fourth option is the correct one, that is 4.77 into 10 raised to minus 10 meter. Okay, the fourth option is the correct answer. Clear? Okay, now the 13th question. Which of the following statements about the nuclear forces is not true? Again, the question is coming as not true. Okay, so carefully read each options. The first option, the nuclear force between two nucleons falls rapidly to zero as their distance is more than a few femtometers. That is the correct one. Okay, then second one, the nuclear force is much weaker than the Coulomb force. Is that option is correct? No, because we already learned that nuclear force is the strongest force in the nature. Okay, so nuclear force is much weaker. So this option is not true. Okay, so the second option is the correct answer. Clear? Okay. So the 14th question. If the reading of the voltmeter V1 is 40 volt, then the reading of voltmeter V2 is. Here the figure is given. The applied voltage is given, that is 50 root 2 sin omega t. Then voltmeter reading V1, that is, it is in between the inductor, okay, and the capacitor. So this is our resistance R, isn't it? So this is a simple LCR circuit, right? Then voltage across inductor and the capacitor is given. Okay, so here the V1 is given, that is V1 equal to 40 volt. Okay, V1 equal to 40 volt. Then we have to find out what is V2. Okay, so here we are going to use the equation that is VRMS square is equal to VR square plus VL minus VC the whole square. Okay, so this is the equation. Okay, so here VRMS square is equal to VR square plus VL minus VC, that is the voltage across the inductor and the capacitor. The difference between the voltage across the inductor and the capacitor is given by V1, right? So V1 is 40. So we have to write this one as 40 square. Okay, now we are going to calculate what is VRMS. For that, we take this one, that is, we have Vm from this one, that is 50 root 2 sin omega t. Vm is 50 root 2. We have the equation for RMS. VRMS is equal to Vm by root 2. That is equal to 50 root 2 by root 2. So root 2 get cancelled. We get VRMS is equal to 50 volt. Okay. So substitute for that. We get 50 square is equal to VR square plus 40 square. Okay. Now, see, VR square, therefore VR square is equal to, okay, we have to write this one as 50 square minus 40 square. 50 square minus 40 square, that is equal to 2500 minus 1600, that is equal to 900. So VR square is equal to 900. Therefore, VR is equal to root of 900, that equal to 30 volt. Okay, so let's go for the option C, the first option, right? So first option is the correct answer, that is 30 volt. Clear? Okay. Then the 15th question. The electric potential V as a function of distance x is shown in the figure. The graph of the magnitude of electric field intensity E as a function of x is. So here the graph is given. Okay. Then in this graph here x. Okay. And y on the y-axis we take the potential. So here we are going for the relation between the electric field and potential, and is given by E equal to minus dV by dx. Okay, minus dV by dx. Okay, then in this case, then consider the time interval, that is the distance, that is 0 to 2. Not time interval, the distance 0 to 2. Okay, here the slope is positive. Right? Here the slope is positive. Then dV by dx gives the slope, right? Okay. So here the slope is positive. Therefore, E become negative. For x equal to 0 to x equal to 2. Okay. E become negative. Okay. Then what about x equal to 2 to x equal to 4? Then that's a constant, right? Then when we take the differentiation, what happens? So that become 0. E become 0. Right? Okay. Then the time interval x equal to, not time interval, the distance x equal to 4 to x equal to 6. Okay. Here the slope is negative. Therefore, E is equal to negative of negative. Right? dV by dx is the slope. Then that quantity is negative, then negative into negative, that is positive, right? So let us go for the options. See, the first option, see, 0 to 2, that is negative. So here is the negative, right? Then 2 to 4, that is 0. See, this is 0. And 4 to 6, that is positive. See, here is positive. So option 1 is the correct answer. Clear? Okay. So next one, the assertion reason type question. The 16th question, assertion. The electrical conductivity of a semiconductor increases on doping. Okay. Yes, that's correct one, isn't it? While doping, the conductivity of the semiconductor will increases. Okay. Then reason doping always increases the number of electrons in the semiconductor. That's wrong statement. Why it's wrong? Because doping is of two types, right? Okay, that is, one is pentavalent. Okay, we have to dope a semiconductor with pentavalent impurity and trivalent impurity. When we dope with pentavalent impurity, the electron will increases. Okay, then what happens in trivalent? Okay, the Hall concentration will increase, right? Okay, so that the reason is wrong. So let's go for the options. See, option C, that is A is true but R is false. Okay, clear? Okay. 17th question. Assertion. In an interference pattern observed in Young's double slit experiment, if the separation D between the coherent sources as well as the distance capital D of the screen from the coherent sources both are reduced 1/3, the new fringe width remains the same. Okay, we have the equation for fringe width, that is beta equal to d lambda by d. Here, for the new fringe width, here d become d/3, right? And small d become d/3. So fringe width remains the same, isn't it? Okay, therefore the assertion is correct. Okay, then reason, fringe width is proportional to small d by d. See, from this equation we have to write beta is proportional to capital D by D, isn't it? So this reason is wrong. Okay, so again option C is the correct answer, that is A is true but R is false. Clear? Okay, now the 18th question. Okay, assertion, the photoelectrons produced by a monochromatic light beam incident on a metal surface have a spread of their kinetic energies. Okay, that's the correct one. Okay, when the photoelectrons and a light falls on a metal surface, okay, what happens? The electron will emit, isn't it? Okay, then reason, the energy of electrons emitted from inside the metal surface is lost in collision with other atoms in the metal. That's correct. Okay, so here the reason, the given reason is the correct explanation of the assertion. Okay, so we have to take the option A as the correct one. That is, both A and R are true and R is the correct explanation of A. Clear? Okay. Now we are move on to the next session, that is section B. Okay. This is the 2-mark questions. Okay. This session, each question carries 2 marks. In this session, we have the internal choices also. Okay. The first one. Electromagnetic waves with wavelength. First one, lambda 1 is suitable for radar systems used in aircraft navigation. Lambda 2 is used to kill germs in water purifiers. Third one, lambda 3 is used to improve the visibility in runways during fog and mist condition. Identify and name the part of the electromagnetic spectrum to which these radiations belong. Also, arrange these wavelengths in ascending order of their magnitude. Okay, so here the first one, lambda 1 suitable for radar systems used in aircraft navigation. Which one is that? Yes, microwave. Okay, microwave. Then second one, okay, lambda 2 is used to kill the germs in purifiers. Which one is that? Ultraviolet. Okay. Then third one, lambda 3 is used to improve the visibility in runways during fog and mist condition. Okay, which one is that? That is infrared. Okay, so these are the waves. Then the first part of the question is over, that is identify and name the part of electromagnetic spectrum to which these radiations belong. Okay, so first one, in radar, it is microwave. For killing the germs, ultraviolet. And improve the visibility in running ways during fog and misty conditions, that is infrared. Now we have to arrange these verbs in different order, right? Okay, in different order. That means, which order is that? Ascending order. We have to arrange these verbs in ascending order. Okay, so we have the electromagnetic spectrum as radio waves, isn't it? Then microwaves, okay? Then IR, visible, then UV, X-ray, and gamma. Okay, these are the electromagnetic radiations. Okay, so here when we go through this right side, here the frequency increases, so that when we move to the left side here, wavelength decreases. Sorry, wavelength increases. Okay. Then now here we are going to arrange the wavelength, okay, in ascending order. Okay, ascending order. So here we have the microwaves. Okay. Then second one, ultraviolet. Okay. Then infrared. Okay. So we have to arrange this one as it is written as, that is lambda, okay, ascending order. So here UV is second one, that is lambda 2 is less than, then next one is IR, that is lambda 3 is less than lambda 1. So this is the order. Okay, lambda 2 less than lambda 3 less than lambda 1. Clear? Okay. So we are moving on to the next one. Question number 20. That is, a uniform magnetic field gets modified as shown in the figure when two specimens A and B are placed in it. The first question, identify the specimen A and B. We have to find out what is A and what is B. Okay. Then from the figure itself, it is clear. In the figure A, the specimen repels the magnetic field. Okay. In which material the magnetic field repels? Okay. That is diamagnetic material. Diamagnetic materials. Okay. Then in B, see, all the magnetic field lines is passing through the specimen, right? Okay, so that one is paramagnetic material. Okay, now go for the second question. This is the first one and second one. Second one is, how is the magnetic susceptibility of specimen A different from that of specimen B? Okay, here we have to find out magnetic susceptibility. Okay, that is, we have to find out chi-em. Okay, chi-em. That is, for diamagnetic material, chi-em have the negative value. Then what about chi-em for paramagnetic? It will have positive value. Okay, so this is the answer of the second of sub-question. Clear? Okay. Then next one, question number 21. What is the nuclear radius of iron 125 if that of aluminum 27 is 3.6 Fermi? Okay, so here the given that the radius, that is, we have the equation for radius R equal to R0 a raised to 1 by 3. Okay, so here we have to write this one as, that is, for iron RFE equal to R0 into what is the mass number of iron? That is 125. Okay, 125 all raised to 1 by 3. That is RFE equal to R0 into 5. Isn't it? Okay, then likewise aluminium. Okay, that is R aluminium equal to R0 into what is the mass number? That is 27. So 27 raised to 1 by 3. Therefore, that is R aluminium equal to R0 into 3. Okay, now take the ratio. I mark this one as equation 1 and this one as equation 2. Now take the ratio, we get RFE by RAL equal to R0 into 5 divided by R0 into 3. So R0 get cancelled, right? Then here the nuclear radius of the aluminum is given, right? So we have to write FE, RFE equal to RAL into 5 by 3. That equal to RAL is given, right? That is 3.6 Fermi. So 3.6 into 5 by 3. So get cancelled, I get 1.2. That equal to 1.2 into 5. That equal to 6 Fermi. Okay. So the radius of the ion is 6 Fermi. Clear? Okay. The next or question, that is the short wavelength limit for the Lyman series of the hydrogen spectrum is 913.4 angstrom. Calculate the short wavelength limit for the Balmer series of the hydrogen spectrum. So the given one is the short wavelength limit of Lyman series, that is short wavelength limit for Lyman series, that is 1 by lambda L equal to R into 1 by 1 square minus the short wavelength is, that is 1 by infinity square. Okay, for short wavelength the values will be infinity, from infinity. Okay, so that is 1 by lambda L is given. What is lambda L? 913.4 angstrom. Okay, is equal to R into 1 minus 0. Okay, right? That is 1 by R equal to 913.4 angstrom. Okay, now we are going to calculate short wavelength limit for Balmer series. Okay, that is lambda 1 by lambda B equal to R into 1 by 2 square minus 1 by infinity square. Right? Okay, so here we have to write it as 1 by lambda B equal to, okay, R into 1 by 4, okay, minus 0. Okay, therefore, here we have to calculate lambda B is equal to 4 by R. That is equal to 4 into 1 by R. That equal to 4 into 1 by R is given, that is 913.4 angstrom. Okay, therefore, the answer is, when we calculate this one, we get lambda B equal to 3653.6 angstrom. So this is the answer. Clear? Okay. The next question, question number 22. A biconvex lens made of a transparent material of refractive index 1.25 is immersed in water of refractive index 1.33. So that lens refractive index NL is given 1.33. Then the refractive index of water is given, lens refractive index is 1.25 and The water refractive index is 1.33. Isn't it? Okay. Will the lens behave as a converging or diverging lens? Okay. Justify your answer. So we have to write the formula of lens maker's formula, that is 1 by f equal to NLW minus 1 into 1 by R1 minus 1 by R2. Okay, that is 1 by f is equal to NLW can be written as NL by NW minus 1 into 1 by R1 minus 1 by R2. Okay, or 1 by f is equal to NL minus NW by NW, okay, into 1 by R1 minus 1 by R2. See, then substitute, we get 1 by f equal to NL, that is 1.25 minus 1.33 divided by 1.33 into 1 by R1 minus 1 by R2. Okay? Clear? Okay. So, from this one, that is here the numerator term is negative. Right? Okay. So, that f become negative. Right? F become negative, isn't it? Okay, then if f become negative, okay, for which lens the focal length is negative? Yes, concave, isn't it? So this one, that is the lens, that is the biconvex lens, when immersed in water having refractive index of 1.33, okay, then that will behave as a concave lens. Okay, it will behave as concave lens. Clear? Okay. Now, question number 23. Okay. The figure shows a piece of pure semiconductor S in series with a variable resistor capital R and a source of constant voltage V. Should the value of capital R be increased or decreased to keep the reading of ammeter constant when semiconductor S is heated? Justify your answer. That means if this semiconductor is heated, okay, what happens? When the semiconductor is heated, its resistivity decreases. Okay, resistivity decreases so that the maximum current will flow through this circuit, isn't it? So, in order to keep the ammeter value constant, okay, ammeter reading constant, okay, what have to do? Then the value of this resistance will be increased. Okay, we have to increase the value of that resistance. Clear? Okay, so this is the answer. Okay, then when the semiconductor heated, the resistivity, what happens to the resistivity? Resistivity decreases so that maximum current will flow through the circuit. Then in order to maintain the ammeter reading constant, we have to increase the value of resistance R. Clear? Okay. So we are moving on to the next question, that is it's OR question. Say, the graph of potential barrier versus width of depletion region for an unbiased diode is shown in graph A. Okay, so here this one is for the unbiased. This graph is for the unbiased one. Okay. Okay. Then, in comparison to A, graph B and C are obtained after biasing the diode. Okay, after biasing the diode, we get these two graphs, B and C. Okay, then in different ways, identify the type of biasing B and C and justify your answer. Okay, here, just look at this graph. This graph is based on the potential, right? Barrier potential. Okay, so we already learned that there are two types of biasing. Which are they? One is the forward biasing and the other one is reverse biasing. Okay, forward and reverse. Okay, in forward biasing, okay, then potential barrier, what happens to the potential barrier? Potential barrier decreases. Okay, that is depletion region decreases, therefore the potential barrier decreases. Then in the case of reverse biasing, okay, depletion region increases, right? Then so that potential barrier increases. Okay, now carefully look at the figures B and C. Okay, B and C, in which one the potential barrier increases. Okay, in the graph B, it is the potential barrier increases, right? So that this graph B, okay, denotes the reverse biasing. Okay, graph B denotes the reverse biasing. Then what about graph C? Graph C is forward biasing. Okay, when we compared with A, then in the graph B, the potential barrier is increased, right? So that it is in reverse biased. Then when we compare with A, the potential barrier in C, it is decreased, so that it is in forward biasing. Clear? Okay. So we are move on to our next question, that is question number 24. A narrow slit is illuminated by a parallel beam of monochromatic light of wavelength lambda is equal to 6000 angstrom. So lambda is given, that is 6000 angstrom. Okay, and the angular width of the central maximum in the resulting diffraction pattern is measured when the slit is next illuminated by the light of wavelength lambda dash. The angular width decreases by 30%. Calculate the value of the lambda dash. We have to calculate what lambda dash. Okay, so for that, here we are going to write the expression for the angular width. That is, angular width is given by 2 phi is equal to 2 lambda by d. This is the equation for angular width. Clear? Okay. Now, in this case, we have to write that is given, that is the angular width lambda dash. When we use the light of wavelength lambda dash, the angular width is decreased by 30%. Isn't it? So new angular width, we have to find out new angular width is equal to, okay, we have to write it as, that is 0.7 into 2 phi. This is the equation for the new angular width. Okay, that is 0.7 into 2 phi, because this is the actual one. Then if it is 30% decreases, that shows 0.7, right? 0.7 into 2 phi. Okay, now we have to calculate what, that is lambda dash, right? So we have to write this one as, that is 2 lambda dash by d is equal to, okay, we have to write it as 0.7 into 2 phi. Okay, therefore we have to write it as 2 lambda dash by d equal to 0.7 into 2 phi, that is 2 lambda by d. So d and d get cancelled, 2 and 2 get cancelled. We get lambda dash is equal to 0.7 into lambda. That is equal to 0.7 into lambda is 6000. That is equal to 4200 angstrom. So new wavelength, that is the value of wavelength, lambda dash is 4200 angstrom. Okay, is it clear? Okay. Now this question number 25. Two large thin metal plates are parallel and close to each other on their inner faces. The plates have the surface charge densities of opposite signs and of the magnitude 17.7 into 10 raised to minus 22 coulomb per meter square. What is the electric field intensity E, first one, in the outer region of the first plate, and B between the plates? Okay, so first of all we have to draw the diagram. That is, there are two plates. Okay, this plate 1 and plate 2. Okay, then one is charged positively, the other one is charged negatively. Okay, then its surface charge density sigma is given. That is, sigma is equal to, what is the value? 17.7 into 10 raised to minus 22 coulomb per meter square. Okay, that's given. Now, this case we already discussed in the chapter electric charges and fields. Okay, then one of the application of Gauss's law, right? So in that case, there we consider three regions, that is, this is region 1, region 2 and region 3. Okay, so if the plates having different types of charges, okay, then outside the plates, that is the outer region of the first plate, okay, that means this region here, okay, the electric field will be 0, E equal to 0. Okay, then next one, between the plates, electric field between the plates is given by the equation E equal to sigma by epsilon 0. Sigma is given, that is 17.7 into 10 raised to minus 22 divided by epsilon 0. Epsilon 0 is 8.854 into 10 raised to minus 12. Okay, 10 raised to minus 12. When we calculate this one, we get the value as 1.99 into 10 raised to minus 10 Newton per coulomb. Okay, Newton per coulomb. Or approximately it can be written as 2 into 10 raised to minus 10 Newton per coulomb. Okay, so these are the answers. Clear? Okay. So we are move on to the next session, session C. Then session C carries 3 marks each. Each question carries 3 marks. Okay. So let's move on to the next question. That is question number 26. Two long parallel conductors carrying currents I1 and I2 are separated by the distance d. If the currents are flowing in the same direction, show how the magnetic field produced by one exert an attractive force on the other. Obtain the expression for this force and hence define 1 ampere. Okay, so first of all, we have to consider two current carrying conductors. Let it be A, carry current in upward direction. Let the current in this conductor is I1. Okay, now let us consider a point P, okay, which is at a distance d from the conductor. Therefore, the magnetic field due to this current carrying conductor, okay, at point P is given by B1 is equal to mu 0 I1 by 2 pi d. Okay, 2 pi d, right? Okay, now we are going to place another conductor at point P, okay, carrying current I2, which is in the same direction. Let this conductor be B. Okay. Now, at point P, that means on this conductor, okay, this conductor is placed in the magnetic field produced by the current carrying conductor A, so that there will exert a force, right? Okay, that force, we have to write it as F21 is equal to, we have the equation BIEL, where L is the length of that conductor. Okay, now here the magnetic field, okay, magnetic field is due to the current carrying conductor A, so that we have to write it as B1. Okay, then here the current, okay, I, okay, that is due to the current in the conductor B, so it is I2. Then L, for both conductors, the L is same. Okay, now we are going to draw the direction of the magnetic field at point P, that is here the current in the upward direction, so that we have to apply the right hand thumb rule. Okay, then when we apply the right hand thumb rule, we get the direction of magnetic field in anti-clockwise direction. Okay, so that the magnetic field will act in this direction. This is the direction of magnetic field. Okay, now we have to calculate the magnitude of the force here, that is F21 equal to, okay, B1. B1 is mu0 I1 by 2 pi d into I2 into L. Okay, therefore F21 is equal to mu0 by 4 pi 2 I1 I2 divided by d into L. So this is the expression for the force. Okay, so first one we find out, that is obtain the expression for this force. Okay, now show how the magnetic field produced by one exert an attractive force on the other. Okay, so here we have to apply the Fleming's left hand rule in order to get the direction of force. So this is the direction of magnetic field, right? So this forefinger points into the board, then current is in the upward direction, right? Then the force, which is act in the direction of the conductor A. Okay, therefore this is the direction of force. This is the direction of force F21, vector F21. Clear? Then if likewise when we consider this conductor, okay, is placed in the magnetic field of B, then okay, magnetic field of B, then here also we have to find out the direction of force. Okay, here when we apply the right hand thumb rule on the conductor B, we get the magnetic field, direction of magnetic field in anti-clockwise direction. In that magnetic field, the conductor A is placed, right? Okay, so that here the magnetic field act in the outward direction. Okay, this is B. Then when we apply the Fleming's left hand rule, okay, that is the magnetic field in outward, okay, the current moving in the upward direction, so that the force acting towards B. Okay, so that this is the direction of F12, that is force on the conductor 1 due to 2. Clear? So from these two directions, that is the direction of F12 and F21, okay, we can see that these two conductors are attract each other. Okay, so that is the answer for this one, that is show how the magnetic field produced by one exert an attractive force on the other. Clear? Then the last one, hence define 1 ampere. So we have to define 1 ampere. Okay, that is 1 ampere current is the current flowing through two parallel conductors in the same direction when they are separated by 1 meter and they experiences a force of 2 into 10 raised to minus 7 Newton per meter in their length. So this is the definition of 1 ampere. Clear? Okay. So our next question, question number 27. The magnetic field through a circular loop of wire 12 centimeter in radius and 8.5 ohm resistance changes with time as shown in the figure. The magnetic field is perpendicular to the plane of the loop. Calculate the current induced in the loop and plot the graph showing induced current as a function of time. So here we have a graph. Okay, from this graph first we have to find out the induced EMF. Then with that induced EMF and the given resistance, we have to calculate the current. Okay, then we have to plot the graph showing the induced current as a function of time. Okay, so for that, first we have to find out the area of that circular loop. Okay, for that, area A is equal to pi r square. Okay, that is equal to, what is the value of pi? That is 3.14 into r. The radius is given, right? That is 12 centimeter. So here we have to convert that centimeter into meter. That is 12 into 10 raised to minus 2 the whole square. That is equal to 3.14 into 12 into 12 into 10 raised to minus 4. Okay, then while we are calculating this one, we get the value as 4, that is equal to 452.14 into 10 raised to minus 4 meter square. So this is the value of area. Okay, so here I am writing this one as area A is equal to 452.14 into 10 raised to minus 4 meter square. So this is the value of area. Okay, now we are going to find out the flux. Okay, then for that flux phi equal to, we have B into A. Okay, magnetic field into area. Okay, here we are taking the maximum flux because they are given the magnetic field is perpendicular to the plane of the loop. So we have to take the maximum flux. Okay, so the induced EMF. Then first we consider the time interval, that is time t equal to 0 to t equal to 2. Okay, then this time interval, that is t equal to 0 to t equal to 2. Okay, then for that, induced EMF equal to, we have the equation minus d phi by dt, that is equal to minus d by dt of B into A, that is a flux. Okay, here the area is constant but magnetic field is varying, right? So that we have to write the induced EMF E is equal to, take the area outside, that is minus A into dB by dt. That is equal to, then give the value of A, that is minus 452.14 into 10 raised to minus 4 into, then dB. dB is the difference of this magnetic field, that is 1 minus 0 divided by time, that is 2 minus 0. Okay, that is equal to minus 452.14 into 10 raised to minus 4 divided by 2. That is equal to, when we divide this one, we get the value as minus 226.08 into 10 raised to minus 4. Okay, that is this much volt. Okay, now we are going to calculate the current in the time interval t equal to 0 to t equal to 2. So current I is equal to, we have the equation, the EMF by resistance, that is equal to, EMF is minus 226.08 into 10 raised to minus 4 divided by the resistance is given, that is 8.5 ohm. Okay, that is equal to minus 224.5 into 10 raised to minus 4 ampere, and this can be also written as, that is equal to minus 2.25 milliampere. So the current for the time interval t equal to 0 to t equal to 2, we get that is t equal to 0 to t equal to 2. Current I equal to minus 2.25 milliampere. Okay, now we are going to calculate the current in the interval t equal to 2 to t equal to 4. Okay, then that is t equal to 2 to t equal to 4. Okay, for that, first we have to find out the EMF, that is E equal to, okay, that is minus d phi by dt, that equal to minus dBA by dt, that equal to minus A into dB by dt, that is equal to. Then from this interval, it is clear that the magnetic field is constant throughout that interval, right? Okay, the value of magnetic field is 1 Tesla. Okay, so that here there is change become 0, that is minus A into 1 minus 1 divided by 4 minus 2, that is E equal to 0 itself. Then what about the value of current? That is I is equal to E by R, that is equal to 0 ampere. Clear? So for time interval t equal to 2 to t equal to 4, the current I become 0 ampere. Okay, then next we consider the next time interval, that is t equal to 4 to t equal to 6. Okay, we get EMF E equal to, that is minus A into dB by dt, that equal to minus 452.14 into 10 raised to minus 4 into dB. dB is, that is change in the magnetic field. The final magnetic field is 0 and initial one is 1. So we have to calculate it as 0 minus 1 by time interval, that is 6 minus 4. Okay, that is equal to minus 452.14 into 10 raised to minus 4. Then here is one negative sign. 0 minus 1 is minus 1. So that minus 1 and this minus 1 become plus. Okay, divided by 6 minus 4, that is 2. Okay, again we get the same value for the EMF, that is E equal to 2 to 6.08 into 10 raised to minus 4 volt. Okay, so this is the value we get. Okay, then finally we have to calculate the current I equal to E by R, that equal to 226.08 into 10 raised to minus 4 divided by 8.5. Then while calculating this one, we get the value as plus 2.25 milliampere. So in the time interval t equal to 4 to t equal to 6, the current I equal to plus 2.25 milliampere. Okay, now we are going to draw the graph between the time interval and the current. Okay, so that we are taking the time along x-axis and current along y-axis. Okay, now the maximum value of current is plus 2.25 milliampere. So that here we have to write it as this current is in milliampere. The maximum value is 2.25 milliampere and the minimum value is minus 2.25 milliampere. Now the time interval, that is 0, then 2, 4, 6. Now we have to draw the graph, that is, okay, for that, for the time interval 0 to 2, the current is minus 2.25 milliampere. So minus 2.25 milliampere, that means up to 2, this is the value of current. Okay, Then in the time interval 2 to 4, that is current is 0. So this is the representation of the current in the time interval 2 to 4. Then for the time interval 4 to 6, what is the value of current? That is 2.25 milliampere. So this is the value. So we have to draw this one as, see, this is the representation of the current. Okay, so we obtain the current time graph as like this. Clear? Okay, so we are move on to our next question. Okay, that is question number 28. An AC source generating a voltage E equal to E0 sine omega t is connected to a capacitor of capacitance C. Find the expression for the current I flowing through it. Plot a graph E and I versus omega t to show that the current is ahead of the voltage by pi by 2. Okay, so here an AC source is applied to a capacitor, okay, having capacitance C. So first of all, we have to draw the diagram. See, this is the capacitor having capacitance C. Then its two ends is connected to an AC source, okay, having EMF E equal to E0 sine omega t. Okay. Then this much voltage when we apply to across the capacitor, then there is a accumulation of charge inside the capacitor, right? Okay, so we already learned that the charge accumulated Q, which is equal to a constant Z into the potential difference, right? Okay, therefore we have to write this one as Q equal to C into, here the potential difference is given as E0 sine omega t. Okay, I mark this equation as equation 1. Okay, for calculating the current, we have to differentiate this equation with respect to t. Okay, therefore when we differentiate, we get dq by dt is equal to d by dt of C E0 into sine omega t. Okay, where C is E0 is a constant, so we had to take it outside. We get d by dt of sine omega t. Okay, now dq by dt is current, so we have to write it as I itself, that is equal to C E0 into, okay, d by dt of sine omega t. What is that? That is cos omega t into omega. Now rearrange this equation, we get omega c into E0 into cos omega t. Therefore I is equal to, okay, this can be also write it as E0 by 1 by omega c into cos omega t. Okay, that is equal to, where this 1 by omega c, okay, is known as XC. Okay, here XC is the capacitive reactance. Okay, XC is the capacitive reactance. Okay, that will act as the resistance of that capacitor. So E0 by the resistance. So what is that? Okay, we get, that is I equal to, okay, E0 by XC into cos omega t. That is equal to E0 by XC is the maximum value of current, that is I0. Okay, that is I equal to I0 into cos omega t. Then voltage applied in terms of sine, right? Okay, then here we have to write this current expression for current in terms of sine also. So we get it as sine I equal to I0 into sine omega t plus pi by 2. So this is the expression for current. Okay, now we are going to draw the waveform of this relation. Okay, for that, first of all, we have to draw the phasor. After that, we have to draw the waveform. Okay, then let us take the maximum voltage V0 in the first quadrant. Okay, then here the current is leads a factor pi by 2, right? Okay, therefore the current will be in the second quadrant. So this is the value of I0. So the angle between V0 and I0 is pi by 2. Okay. Now we have to draw the graph. Okay. Let us take, this is the maximum value of current, that is I0, and this is the maximum value of voltage, V0. Okay, now we have to draw the graph. Okay, this is the graph for the applied voltage, that is the maximum voltage, and for the current, we have to draw like this. Okay, so this is the shape of the graph. Clear? Okay, now we are move on to the next question. See, it's an OR question. So an AC voltage V equal to V0 sine omega t is applied across a pure inductor of inductance L. Find an expression for the current I flowing in the circuit and show mathematically that the current flowing through it lags behind the applied voltage by a phase of pi by 2. Also draw the graph for V and I versus omega t for the circuit. Okay, so here also there is an inductor, right? Okay, so draw the diagram for the inductor, that is, this is our inductor having inductance L, which is applied. Its two ends are applied to a AC source, that is V equal to V0 sine omega t. Okay. Now, we have the equation, that is V equal to, okay, L into di by dt. Okay. This equation is familiar to you, right? Okay. Then from this, di equal to V by L into dt, right? Okay. Therefore, I equal to, we have to integrate this one, that is integral V by L into dt, right? Therefore, I is equal to, okay, here V is V0 sine omega t by L into dt. That is equal to V0 by L into integral sine omega t into dt. Right? Okay. Therefore, we have to write current I is equal to V0 by L into, what is integral sine omega t dt? That is minus cos omega t by omega. Okay, therefore I is equal to minus V0 by omega L into cos omega t. Okay, where omega L is equal to XL, that is called inductive reactance. Okay, therefore the equation for current become I is equal to minus V0 by XL into cos omega t, where XL acts as the resistance for the inductor, right? Okay, then here V0 by XL, that can be written as minus I0 into cos omega t. Here we have to change that cosine term into sine term. Okay, then we get I is equal to I0 into sine omega t minus pi by 2. See. So, from this equation, it is clear that the current lags behind the EMF by a factor pi by 2. Okay. Now we have to draw the phasor diagram and the graph. Okay. Okay. Here we are taking this is omega t. Okay. Then this is V0. Okay. Then here the current lags behind the EMF, so that this comes to the fourth quadrant. This is our I0. This angle is pi by 2. Clear? Okay. Now we have to draw the graphical representation. Okay. See, this is the graphical representation of applied voltage. Then what about the current? Okay. We have to draw from here. Okay. So this is the graphical representation of current. Now we have to, if we need, we have to draw the maximum voltage and maximum current also here. Okay, clear. Okay, now we are move on to the next question. Question number 29. That is, radiation of frequency 10 raised to 15 Hertz is incident on 3 photosensitive surfaces A, B and C. The following observations are recorded. Surface A, no photo emission occurs. Surface B, photo emission occurs but photoelectrons have zero kinetic energy. Then surface C, photo emission occurs and photoelectrons have some kinetic energy. Using Einstein's photoelectric equation, explain the 3 observations. Okay, so we know the Einstein's equation, that is h nu equal to h nu 0 plus kinetic energy. This is Einstein's photoelectric equation, right? Then for the surface A, okay, for surface A, no photoelectric emission occurs. Okay, there is one condition for photoelectric emission occurs. What is that condition? Yes, the radiation should have the threshold frequency, right? The radiation have the frequency more than the threshold frequency, then only the photoelectric emission occurs, right? Okay, therefore, in surface A, no photoelectric emission occurs means this surface having large value of threshold frequency compared with the incident frequency. Okay, that means for the surface A, threshold frequency is greater than 10 raised to 15 Hertz. Okay, that's why there is no photoelectric emission occurs. Then for surface B, photoelectric emission occurs but the photoelectrons have zero kinetic energy. Okay, so then from this equation, we have to write the kinetic energy is equal to h nu minus h nu 0. Okay, that is equal to h into nu minus nu 0. When will be the kinetic energy 0 in this case? Okay, then when nu equal to nu 0, okay, then kinetic energy become 0, right? That means in the second case, the frequency and the threshold frequency having the same value, okay, but at that time the kinetic energy become 0. Clear? Okay, then surface C, okay, for the surface C, okay, photo emission occurs and photoelectrons have some kinetic energy. Okay, that means they obey this law, that this equation, isn't it? Okay, in that case, then there is the surface C having threshold frequency less than 10 raised to minus 15 Hertz. That means there is emission of photoelectrons. Okay, clear? Okay, so we are moving on to the next question. That is, this is the OR question. Okay, that is, the graph shows the variation of photocurrent for the photosensitive metal. What does X and A on the horizontal axis represent? Okay, this is the first question. What does X and A on the horizontal axis represent? Okay, see, here is a graph is shown, so we have to find out what is X and what is A. Okay, that is, here A is the stopping potential. Okay, as you know, okay, stopping potential. Okay, or it is also called cutoff voltage, right? Okay, then X is collector plate potential. Collector plate potential. Okay, then question B. Draw this graph for 3 different values of frequencies of radiation, incident radiation, nu1, nu2 and nu3. Then given that nu3 greater than, nu2 greater than nu1 for the same intensity. Okay, this is the direct question. Okay, so we have to draw the graph. Okay. This is the collector plate potential. And this is photocurrent. Okay. Now, in different frequencies, we get for the same intensities, we get the graph like this. This is the same intensity I. Okay, for the same intensity, we get the graph like this. This graph is very familiar to you, right? Okay, so this is for nu 1, this is nu 2, and this is our nu 3. Here, nu 3 greater than nu 2 greater than nu 1. Okay, then this is V01, this minus sign, minus V02, then here it is minus V03. Okay, clear? That means for the different frequency, there is a different stopping potentials. Clear? Okay, so this is the answer for sub-question B. Then for the sub-question C, draw this graph for 3 different values of intensities of incident light I1, I2 and I3. I3 greater than I2 greater than I1 having the same frequency. Okay, frequency is same but intensity is different. Okay, if the frequency is same but the intensity is different, okay, so this is the collector plate potential. And this one is photocurrent. Okay, then the graph is like this. Okay, this is for the first one, second intensity, and the third one. This is I1, I2, and I3. Here, the stopping potential V0 is same. Okay, here the graph for I3 greater than, I2 greater than, I1. Then in this graph, the frequency is same. That's why the stopping potential is same for all the intensities. Clear? Okay. So this is the answer for the sub-question C. Clear? Okay. Now the 30th one. The ground state energy of the hydrogen atom is minus 13.6 electron volt. The photon emitted during the transition of electron from n equal to 3 to n equal to 1 state is incident on the photosensitive material of unknown work function. The photoelectrons are emitted from the material with the maximum kinetic energy of 9 electron volt. Calculate the threshold wavelength of the material used. Okay, so here we are going to use the equation, Einstein's photoelectric equation, that is H nu equal to H nu 0 plus Ke. This is our equation. Okay, so from this equation, first we have to calculate what is H nu. Then after that, we calculate H nu 0. Okay, then for calculating H nu, they are given the transition of electron from n equal to 3 to n equal to 1. Okay, then for that, that is, we have the equation according to Bohr's third postulate, E equal to EI minus EF, right? That is, E is H nu is equal to EI, that is minus 13.6 divided by initial, it is 3, that is 3 square minus 13.6 divided by 1 square, right? Okay, therefore, that is equal to 13.6 into 1 minus 1 by 9, right? Okay, that is H nu equal to 13.6 into 9 minus 1 by 9. That equal to, we get the value as, we get it as, when we calculating this one, we get 12.1 electron volt. H nu, we get the value as 12.1 electron volt. Clear? Okay, so we get the value as H nu is equal to 12.1 electron volt. Okay, then now we are going to calculate what is h nu 0. Okay, so h nu 0 is the work function. H nu 0 is equal to h nu minus Ke. That is equal to h nu is 12.1 minus kinetic energy is given, that is 9 electron volt, right? Okay, 9 electron volt, that is equal to, we get the value as 3.1 electron volt. So the work function, we get 3.1 electron volt. Clear? Okay, now from this we have to calculate what is the value of threshold wavelength. Okay, for that, h nu 0 can be written as c by lambda 0 is equal to 3.1 electron volt. Okay, 3.1 electron volt. From this, lambda 0 is equal to hc by 3.1 into, convert that electron volt into joule, we get 1.6 into 10 raised to minus 19. That is equal to h value 6.63 into 10 raised to minus 34 into 3 into 10 raised to 8 divided by 3.1 into 1.6 into 10 raised to minus 19, and that is equal to, we get the value as 4 into 10 raised to minus 7 meter. While calculating, we get the value of lambda 0, that is threshold wavelength, as 4 into 10 raised to minus 7 meter. Clear? Okay. So we are move on to our section D. Okay, then this section D, each question carries 5 marks. That means this is an essay question. Okay, this session carries essay questions. Okay, so the first question, okay, 31st question, draw equipotential surface for first one an electric dipole and second one two identical positive charges placed near each other. Okay, so for that, the first one, an electric dipole, the electric dipole consists of a positive charge and a negative charge, right? Okay, while drawing the potential equipotent surface, we have to draw like this. Okay, this is the representation of equipotential surface for an electric dipole. Then second one, for identical positive charge. Okay, for identical positive charge, that means both are the positive charges. Okay, in both are positive charges, see here is a repulsion, that is this also you have to draw like this. Okay, so these are the representation of two identical positive charges placed near each other. Clear? Okay, then next one. In a parallel plate capacitor with air, this is the second question, that is sub question B. In a parallel plate capacitor with air between the plates, each plate has area. The area is given A equal to 6 into 10 raised to minus 3 meter square, and the separation between the plate is 3 millimeter. That is D is equal to 3 millimeter. That is equal to 3 into 10 raised to minus 3 meter. Okay. Calculate the capacitance of the capacitor. So we have to just write the equation for capacitance of parallel plate capacitor, that is E is equal to epsilon 0 A by D. This is the expression for capacitance of a parallel plate capacitor. That is equal to 8.865 into 10 raised to minus 12 into area is 6 into 10 raised to minus 3, the whole divided by D, that is 3 into 10 raised to minus 3. Okay, so 3 and 6 get cancelled, we get 2, that equal to. Okay, while calculating this one, we get 8.865 into 2, that is 10 1 we get 17.730 into, so 10 raised to 3, 10 raised to get cancelled, we get 10 raised to minus 10, that is equal to, we get the value as 17.730 into 10 raised to minus 10, okay, 10 raised to minus 10. So this is the value, this much farad. Okay, this much farad. Clear? So this is the value of the capacitance. Then we move on to the OR question. Okay. See, the three charges minus Q, capital Q and minus Q are placed at equal distances on a straight line. If the potential energy of the system of these charges is 0, then what is the ratio of Q is to Q? So first of all, we have to draw the diagram. For that, this is our minus Q, okay, and this is minus Q, and this is our capital Q. All these are placed at the same distance, let it be x. That is, the distance between minus Q and capital Q is x, capital Q and minus Q also x. Okay. Therefore, in this case, first of all, we have to find out the total potential energy, that is equal to, okay, 1 by 4 pi epsilon 0, potential energy between minus Q and Q, okay, to minus Q into Q divided by x. The next one, potential energy between Q, capital Q and minus Q, that is equal to 1 by 4 pi epsilon 0 minus Q, capital Q by x. Then potential energy between minus Q and minus Q, that is equal to 1 by 4 pi epsilon 0 minus Q into minus Q by the distance between minus Q and minus Q is 2x. Okay, then they are given the sum of the potential energy, okay, that means that is 0. Okay, so we have to write it as 1 by 4 pi epsilon 0 into, okay, do here the 1 by 4 pi epsilon 0 is common, right? So we have to take it outside, into minus Q by x plus minus Q by x plus Q square by 2x is equal to 0. Okay. Now, can be also written as, this is minus 2Q by x plus Q square by 2x is equal to 0. From this, Q square by 2x is equal to, take this minus 2Q by x to the right hand side, we get 2Q by x. Therefore, x and x get cancelled, 1Q and 1Q get cancelled. Okay, now we have to find out the ratio Q by Q. Okay, this Q divided by Q, okay, that is equal to 1 by 4. So, ratio is 1:4. So, this is the answer for the first question. Clear? Okay. Now, the second one, obtain the expression for electric field intensity due to uniformly charged spherical shell of radius r at a point distance r from the center of the shell outside it. Okay, this one is very familiar to you by using the Gauss's theorem. Okay, let us consider a spherical shell having radius capital R, okay, which is charged positively on its surface uniformly. Okay, now let us consider a point P which is at a distance r from the center of the sphere. Okay, so in order to calculate the electric field intensity at point P, we have to draw a Gaussian surface that you know. Okay, then let us consider a small area here. Okay, at this, the electric field, direction of electric field in outward direction because it's a positive charge. Okay, then area vector is also directed, right, in the outward direction. Okay, therefore, flux through that small area is given by d phi equal to vector E dot ds, that is equal to E ds cos theta, that is equal to E ds cos 0, that is equal to E ds. Okay, when we consider the entire Gaussian surface, we have to write it as phi is equal to, that is E into sigma all ds into ds, that is equal to E into sigma all ds can be written as S. Okay, that is equal to E into 4 pi r square. So this is our equation 1. Okay, now we are going to take this one as, okay, that is the flux phi equal to Q by epsilon 0. According to Gauss's theorem, flux phi equal to Q by epsilon 0. Therefore, we have to change this Q in terms of surface charge density. We have the equation sigma is equal to Q by S, right? Okay. Therefore, Q is equal to sigma into S, that equal to sigma into 4 pi. Here we have to take it as the radius of the sphere, okay, because we are charging on the surface of that sphere. Okay. So substitute in that equation, we get phi equal to sigma into 4 pi r square by epsilon 0. Mark this equation as equation 2. Okay. Now we are going to compare equation 1 and 2 because for the equation 1 and 2, left hand sides are equal, right? Okay. So we have to equate the RHS side. Okay. Therefore, we get it as E into 4 pi r square is equal to sigma into 4 pi capital R square by epsilon 0. So here 4 pi get cancelled. We get equation for electric field E equal to sigma r square by, okay, epsilon 0 r square. So this is the expression for electric field. Clear on the outside surface. Okay. And next one, draw the graph showing the variation of electric field intensity E with R for R is greater than capital R and R is less than R. Okay, for that, first we have to draw a sphere like this. Okay, this is the center of the sphere and this distance is capital R. Okay, now we are going to draw the graph. Okay, this is the center O. Okay, so this much distance is capital R. Okay, this distance is capital R. Okay, from here it is R. Okay, now when we draw the graph, okay, then inside the sphere electric field is 0, right? Okay, then we have to draw this one as inside the sphere the electric field is 0. Okay, then before that we have to mark the electric field E here and this is the distance. Okay, so electric field is 0. Okay, inside the sphere electric field is 0. Then outside sphere at the surface the field become maximum. Okay, then when the distance increases then the field decreases. Okay, so we have to draw on the left hand side also, okay, like this. Okay, then this part is here the capital R is less than R, okay, and then inside, that is this part, is capital R is greater than R. Okay, clear? Okay. So we are moving on to the next question, 32. Question number 32. Explain the term drift velocity of electrons in a conductor. Okay, as you know, okay, that is, suppose a conductor is placed, suppose we have a conductor like this. Okay, if we apply potential drop V, okay, what happens? All the electrons will be drifted towards the positive end of the conductor. Okay, so we have to define the drift velocity. That is, drift velocity is the average velocity of the electrons with which all the electrons in the conductor is drifted towards the positive end of the conductor. Okay, so that is the definition for drift velocity. Then hence obtain the expression for current through the conductor in terms of drift velocity. Okay, then for that we have the equation for current I equal to Q by T. Here first we have to find out what is Q. See, for that, let small letter n be the number of electrons per unit volume of the conductor. Then if we assume that conductor is a cylinder, the volume is Al. Therefore, the total number of electrons is equal to n into Al. Okay, therefore total charge Q is equal to n into Al, that is total number of electrons into one electronic charge E. Okay, now we have to calculate the time also. Time, that is T is equal to distance by velocity. Okay, here the distance is the distance of this conductor, we take it as L. So that is L by, here velocity is Vd. Okay, that is the drift velocity. Okay, then on substituting we get that is equal to NALE by L into Vd. Therefore, L and L get cancelled. We get the expression for drift velocity and current as I is equal to NAVD into E. So this is the relation. Clear? Okay, now the next one is two cells of EMF E1 and D2 and internal resistance R1 and R2 are respectively connected in parallel as shown in the figure. Deduce the expression for first one, the equivalent EMF of the combination. Second one, equivalent internal resistance of the combination. Third one, potential difference between the points A and B. Okay, before that, we have to write the expression for current, that is I1 is equal to E1 minus V by R1. Okay, then what about I2? That is I2 is equal to E2 minus V by R2. Okay, now therefore total current I is equal to I1 plus I2, isn't it? Okay, therefore we get I is equal to, that is equal to E1 minus V by R1 plus E2 minus V by R2. Okay, therefore I is equal to this much, that is equal to E1 by R1 plus E2 by R2 minus V into 1 by R1 plus 1 by R2. Okay, so I is given by write this. Okay, then from this equation we have to write V equal to, okay, V into 1 by R1 plus 1 by R2, that is take the LCM as R1 R2, we get R1 plus R2 divided by R1 R2 is equal to, okay, E1 by R1 plus E2 by R2 minus I. Okay, therefore V is equal to, we have to write it as E1 R2 plus E2 R1 the whole divided by R1 plus R2, okay, minus I into R1 R2 divided by R1 plus R2. Okay, suppose that combination, that means this combination we have to assume it is in a single cell, as a single cell having EMF E equivalent and internal resistance R equivalent. Therefore, the terminal potential difference V can be written as V equal to E equivalent minus I R equivalent. Okay, then I mark this equation as equation 1 and this one as equation 2. Then okay, compare equation 1 and 2. Okay, from equation 1 and 2 we have to write it as E equivalent is equal to, okay, we get E1 R2 plus E2 R1 divided by R1 plus R2. Okay, now next one, R equivalent is equal to R1 R2 divided by R1 plus R2. Okay, so we get the expression for equivalent EMF and equivalent resistance. Okay, so this is our first question. Okay, and the second one, R equivalent, is our second question. Answer for the second question, right? Okay, then third question, potential difference between the points A and B. Okay, so we know that for the parallel connection, potential difference is same. Okay, so that for the third question, the answer is, we have to write it as the potential is same, or we have to write it one as V equal to E equivalent minus I R equivalent. Okay, this one is the answer. Clear? Okay. Now we are move on to the next one. State two Kirchhoff's rules used in the analysis of electric circuit and explain them. Okay, first law. Okay, first Kirchhoff's law, which is very familiar to you, right? Okay, so the junction rule. Okay, what is that? At any junction of electric circuit, the algebraic sum of entering currents and leaving currents is to be 0. Okay, that is, here we consider a junction here in which the current I1 and current I2 and current I3 is coming to the junction, and current I4 is leaving from the junction. Okay, according to the sign convention, we have to write the currents which is entering into the junction, we have to add that currents, and if the current is leaving from the junction, we have to take it as negative, that is subtract it. That is equal to 0. Okay, then next one, loop rule, that is, in any closed loop involving resistors and cells, the algebraic sum of potential is 0. Okay, that means sigma delta V equal to 0. Okay, for that we have to consider a circuit which consists of cells and resistors. Okay, here the cell having EMF E1, this is E2, this is R1, R2 and R3. Okay, then in this case, let I1 be the current flowing from E1 and I2 be the current flowing from E2. At this junction, it meet together, and I1 plus I2 current will be flowing through R2, and at this junction, that current will be flowing as to E1 it is I1 and to E2 it is I2. Okay, for calculating, it is, we consider the loop as A, B, C, D, E, F. Okay, so first loop, we have to calculate loop A, B, E, F, A. Okay, A, B, E, F, A. For that, we have to write this one as I1 plus I2 into R2, then plus R1 into I1 minus E1 equal to 0. Okay, this is our first linear equation. Okay, from the loop A, B, E, F, A. Then from the loop B, C, D, E, B. Okay, then we have to write it as E2 minus R3 into I2 minus I1 plus I2 into R2 equal to 0. So this is the second linear equation. Then while solving these two linear equations, we will get the value of currents, that is I1, I2 and I3. Clear? Okay. Now, next one, derive the equation for the balanced state in a Wheatstone bridge using Kirchhoff's rule. Okay, so for that we have to draw the Wheatstone bridge. P, Q, R, S. Okay, this is our galvanometer having resistance G, and this is key K1. Okay, now this is a cell EMF having EMF E and a key K2. Okay, now we are marked this one as this loop as A, B, C, D. Okay, then if we close this key K2, okay, current I will flow through the circuit, right? Current I will flow through this circuit. Okay, at this junction, let I1 be the current flowing through P, and the remaining current, that is I minus I1, with the current flowing through R. Okay, then at this junction, again I1 is divided into 2, one current is flowing through Ig, that is galvanometer, and the remaining current, that is I1 minus Ig, flowing through Q. Then when we close this key, then here the current Ig and the current I minus I1 will meet, and it flows through as I minus I1 plus Ig through S. Okay, then at this junction both the currents will meet and flows as I. Okay, now here we consider, for finding out the balanced condition, we consider the loop A, B, D, A. A, B, D, A, this loop, A, B, D, A. Okay, for that, okay, we have to write it as I1P, okay, plus IgG, okay, then minus I minus I1 into R equal to 0. This is our equation 1. Okay, now consider the another loop, loop BCDB. Okay, which is that loop BCDB. Okay, for that loop we have to write it as I1 minus Ig into Q. Okay, then minus I minus I1 plus Ig into S minus Ig into G equal to 0. This is our equation 2. Okay, in order to adjust this R, the value of R, so that the galvanometer shows null deflection. Okay, therefore in that case we have to take Ig equal to 0. Okay, now the equation 1 becomes, okay, now I'm write this diagram. Okay, now equation 1 becomes I1P, right, minus I minus I1 into R equal to 0. Or we have to write it as I1P equal to I minus I1 into R. I mark this equation as equation 3. Okay, then equation 2 becomes, we have to write it as I1Q, okay, because Ig becomes 0, right? Okay, minus I minus I1 into S equal to 0, or I1Q is equal to I minus I1 into S. This is our equation 4. Okay, now divide equation 3 by 4. We get I1P by I1Q is equal to I minus I1 into R by I minus I1 into S. So I1 get cancelled, I minus I1 get cancelled. We get P by Q is equal to R by S. So this is the balanced condition for Wheatstone bridge. Clear? Okay. Now, next one, question number 33. Draw the graph showing intensity distribution of fringes with phase angle due to the diffraction through a single slit. What is the width of central maximum in comparison to that of a secondary maximum? Okay, so listen. First of all, we have to draw the graph for intensity distribution. In y-axis, we take intensity, and here we take the angle, okay, diffraction angle. Okay, then while we are drawing this graph, it's a diffraction pattern, so the amplitude will decreases. Okay, here also the amplitude will decreases. Okay, so this is the shape of the graph. Clear? Okay, now then second question, what is the width of the central maximum in comparison to that of secondary maximum? Okay, we have the equation for width of central maximum as, okay, twice of secondary maximum. Okay, twice of the secondary maximum. Okay, so that is the answer for the second question. Okay, our next question is a ray PQ is incident normally on the face AB of a triangular prism of refracting angle 60 degree as shown in the figure. The prism is made up of a transparent material of refractive index 2 by root 3. Trace the path of the ray as it passes through the prism. Calculate the angle of emergence and angle of deviation. Okay, so first of all, we have to draw the ray diagram. This is our prism, okay, that is A, B and C. Okay, now a ray PQ incident normally on the prism, right? Okay, so for that, let us consider this is the ray. Okay, I mark this ray as PQ. So it makes an angle 90 degree, right? Okay, normally. So if it is normally incident, then that ray will pass through the prism without any deviation. Okay, so that we have to draw that one as like this. Okay, see, this is the ray. Okay, clear? Then, and it will strikes on the face AC. Okay, see, at AC we have to draw the normal again. See, this is the normal. Okay, now see here the angle of the prism, it is an equilateral triangle, so this is 60 degree, right? Then what about this one? This angle is 90 degree. Okay, then this is a triangle, right? Okay, so in this triangle, the sum of these two angles is 150. Okay, then what about the remaining this one? This is 30 degree, right? So if it is 30 degree, what about this angle? This angle is 60 degree, right? Okay, now we are going to calculate what is the angle of emergence. Okay, for that, here we have to find out the critical angle. Okay, why we have to find out the critical angle? Because the ray is traveling from denser medium to rarer medium. So we have to find out the critical angle by using the equation, that is n is equal to 1 by sine IC. Okay, n equal to 1 by sine IC. Okay, from this, sine IC is equal to 1 by n. Okay, then here, according to the question, the refractive index of the material prism is given, that is 2 by root 3. Okay, so n is given, that is 1 by 2 by root 3. That is sine IC is equal to root 3 by 2. Or IC is equal to, okay, sine inverse of root 3 by 2. Okay, that is equal to, okay, then sine inverse of root 3 by 2. So what is the angle that? That is sine 60 degree. Like, that is IC is equal to 60 degree. So the critical angle of the prism is, we get it as 60 degree, right? So see, this ray is incident at an angle 60 degree. That means the ray will incident on the surface AC at the critical angle, so that this ray will emerge out, just grazes through the surface. Okay, so it makes an angle 90 degree. Is it clear? So that the angle of emergence E, we have to write it as angle of emergence E equal to 90 degree. Okay, so now we already answered the two questions, that is trace the path of the ray as it passed through the prism. So it's already done. Okay, then calculate the angle of emergence. Angle of emergence is already done. Then next one, angle of deviation. Next we have to find out angle of deviation. Okay, angle of deviation delta equal to I plus E minus A. This is the expression for calculating the angle of deviation, that is equal to angle of incidence, it is 0, plus angle of emergence, that is 90 degree, minus angle of the prism, that is 60. Therefore, angle of deviation delta equal to 90 minus 60, that is equal to 30 degree. Okay, so we get the angle of deviation as 30 degree and angle of emergence as 90 degree, and we complete, and the critical angle is 60 degree, and we complete this red diagram, right? Clear? Okay, so we are move on to the next one, that is OR question. Write 2 point of difference between an interference pattern and a diffraction pattern. Okay, so interference pattern and diffraction pattern. So here we have to write 2 point differences between interference and diffraction. Okay, so in interference, the intensity of the bright and dark bands are same. Then what about the diffraction? Okay, then intensity is different. Okay, then second point difference, in interference, each band having the same width. Okay, but in diffraction, the bandwidth is different. Clear? Okay, then next one is a ray of light incident on the face AB of equilateral glass prism shows minimum deviation 30 degree. Calculate the speed of light through the prism. Okay, for that, here they are given deviation delta equal to 30 degree. Okay, now we have to calculate the speed of light through the prism. For that, we are using the equation n equal to sine A plus delta by 2 by sine A by 2. Okay, then we know that n equal to C by V. Okay, we have to write it as C by V equal to sine A, 60 plus 90. Okay, that is 60 plus delta is 30. That is 60 plus 30 is 90 by 2. That is 45 by sine A by 2. That is sine 60 by 2. That is 30. Okay, from this, I have to write V equal to, okay, V equal to C into sine 30 by sine 45. That is equal to C. That is 3 into 10 raised to 8 into sine 30 is half into sine 45. Okay, sine 45. What is the value of sine 45? 1 by root 2. So it is root 2. So here we have to cut it as it is root 2. That is V equal to 3 by root 2 into 10 raised to 8 meter per second. So this is the value of velocity. Okay, no need to calculate this value. Clear? Okay, then next one. Find the angle of incidence at face AB so that the emergent ray grazes along the face AC. Here we have to find out the angle of incidence. For that, we have to draw the ray diagram. Okay, see, let us consider a ray, okay, which is incident on the face AB. Okay, now we have to draw the normal here. Let this angle be I, that is angle of incidence. Okay, then it bends towards the normal and strikes on the face AC. Here the angle R1. Okay, then again we have to draw the normal here. This angle we take it as R2. Then according to our question, the emergent ray grazes along the face AC. That is, this is the condition. So this angle is 90 degree. Okay, therefore this R2 is our critical angle. First we have to find out that critical angle by using the equation. Okay, that is n is equal to 1 by sine IC. Instead of this IC, we have to write it as R2. Okay, therefore sine R2 is equal to 1 by n. Now we have to calculate what is the refractive index. Okay, that is n is equal to, we have the equation C by V. That is equal to 3 into 10 raised to 8 divided by V. We already get it as that is 3 by root 2 into 10 raised to 8. That is 3 by root 2 into 10 raised to 8. So 3 and 3 get cancelled, 10 raised to 8, 10 raised to 8 get cancelled. We get n equal to root 2, right? Okay, then on substituting, we get sine R2 is equal to 1 by root 2. Therefore, R2 is equal to sine inverse of 1 by root 2, that is equal to 60 degree. So, the value of R2 is 60 degree. Clear? Okay, now we have to calculate the value of I. For that, we are using the equation n is equal to sine I by sine R. Okay, this formula is familiar to you. That is Snell's law of refraction, right? Okay, so here we have to find out this I. Okay, but R is not given, right? So first of all, we have to find out this R1. Okay, then only we have to find out the I. Okay, then in order to find out R1, this R2, we have to find out R2 first. Okay, for that, see here this refracted ray makes an angle 90 degree. Okay, so this R2 we have to consider it as what? Our critical angle. For that, we have to use the formula n is equal to 1 by sine IC. Okay, here that is equal to 1 by sine R2. Okay, therefore sine R2 is equal to 1 by n, isn't it? Okay, therefore R2 is equal to 1 by n, that is sine inverse of 1 by n. Okay, that is equal to sine inverse of 1 by root 2. Okay, therefore R2 is equal to, okay, that is 45 degree, right? R2 is equal to 45 degree. Clear? Okay, therefore we get the value of R2. Now we have to calculate what is R1 by using the equation. Here I am writing the value of R2 as 45 degree. Okay, now I'm going to find out the value of R1 by using A is equal to R1 plus R2. We have the equation. Okay, that is R1 equal to A minus R2, that equal to 60 minus 45. That is equal to R1 equal to 15 degree. Okay, so R1 is, we get it as 15. Now we have to substitute in that equation. So here R1 equal to 15 degree. Okay, therefore sine I is equal to n into sine R. That is equal to, the value of n is given, that is root 2 into sine R is 15 degree, sine 50. Okay, therefore I is equal to sine inverse of root 2 into sine 15. So this is the answer. Clear? Okay, so we are move on to our next one. So the last two questions are based on case studies. The first question, that is question number 34. Case study, read the following paragraph and answer the questions. See, a number of optical devices and instruments have been designed and developed, such as periscope, binoculars, microscope, and telescopes, utilizing the reflecting and refracting properties of mirrors, lenses, and prisms. Most of them are in common use. Our knowledge about the formation of images by the mirrors and lenses is the basic requirement for understanding the working of these devices. So these are the given passage. Okay, then based on that passage, the first question is why the image formed at infinity is often considered most suitable for viewing. Explain. Okay, then it reduces the strain of our ciliary muscles. Okay, it's a very easy question, right? See, when the image is formed at infinity, we can see it with minimum strain. Okay, that means without strain in the ciliary muscles of the eye. Okay, then second question, in the modern microscope, multi-component lenses and are used for both the objective and the eyepiece. Why? Okay, so this is also a very interesting question, okay, and also very easy. Okay, this is because for getting the high quality images. Okay, say the multi-component lenses are used for both objective and eyepiece to improve the image quality. Okay, by minimizing the various optical aberrations in the lenses. So you already learned about the several types of aberrations, right? Okay, chromatic aberration, right? Spherical aberrations like that. Okay, so in order to reduce that one, we have to use the multi-component lenses. If the aberrations are reduced, we get the high quality images. Okay, so next one, write 2 points of difference between compound microscope and astronomical telescope. Okay, the first one, the compound microscope is used to observe minute nearby objects. Okay, then whereas the telescope is used to observe distant objects. Then next one, the compound microscope of focal length of objective is lesser than that of the eyepiece, whereas in telescope, the focal length of the objective is larger than the eyepiece. Okay, see, in compound microscope, the focal length of objective is lesser, okay, than that of the eyepiece. Okay, then whereas in telescope, focal length of the objective is larger. Okay, these are the two differences. Clear? Then next one, write, this is the OR question for the third sub question, that is write 2 distinct advantages of a reflecting type telescope over a refracting type telescope. See, the first one is the image formed by the reflecting type telescope is brighter than that of the refracting type telescope. Okay, in reflecting type telescope, the image we get, the image is being brighter, okay, than the refracted one. Okay, then the second one is the image formed by the reflecting type telescope is more magnified, okay, than they're formed by the refracting type. That means we get the image from the reflecting type telescope, okay, which is more magnified than the refracting type telescope. Okay, clear? Okay, then the second one, the last question, okay, the case study light emitting diode. Read the following paragraph and answer the questions. LED is a heavily doped PN junction which under forward bias emits spontaneous radiation. When it is forward biased, due to the recombination of holes and electrons at the junction, energy is released in the form of photons. In the case of silicon and germanium diode, the energy released in the recombination lies in the infrared region. LEDs that can emit red, yellow, orange, green, and blue light are commercially available. The semiconductor used for fabrication of visible LEDs must at least have a band gap of 1.8 electron volt. The compound semiconductor gallium arsenide phosphide is used for making LEDs of different colors, okay, and LEDs of different kinds. Okay, our first question. Why are LEDs made up of compound semiconductor and not for elemental semiconductors? Okay, that means LEDs are always made up of compound semiconductors. Okay, not as elemental semiconductors. Okay, so the answer is LEDs are made up of compound semiconductors and not by the elemental semiconductor because the band gap of elemental semiconductor has a value that can detect the light of wavelength which lies in the infrared region. That means the band gap of elemental semiconductors, okay, which detect what? Infrared region, the wavelength of infrared region. Okay, the light of wavelength of infrared region will be detected by the elemental semiconductors because they have the band gap in that range. Clear? Okay. Then next one, what should be the order of band gap of an LED if it is required to emit light in the visible range? Okay, we have there are available most of the LEDs like blue color or yellow or green, like that, right? Okay, so in that cases, what about the band gap? Okay, here the band gap is 1.8 electron volt to 3 electron volt. This is the range of the band gap. Then third question. A student connects a blue colored LED as shown in the figure. The LED did not glow when switch S is closed. Explain why. Okay, so carefully observe this figure. If that student close this switch S, okay, what happens? The current will flow, right? Right? Is this possible? No. Why? Because when we look at the biasing of this LED, okay, here the negative terminal of the battery is connected to the P side of the diode and positive is connected to the N side. That shows this diode is connected in reverse bias. Okay, so that there is no flow of current. Clear? Okay, then next one. Draw the VI characteristics of PN junction diode in first one forward bias and second one reverse bias. Okay, then when the diode is in forward bias, that is, this is the connection for forward biasing, right? Okay, in that case, when we draw the graph, okay, between the voltage and current. In forward bias, the current is measured in milliampere. Okay, then initially, okay, the current will be 0. When the voltage increases, current will be 0. When it reaches a particular voltage, okay, the current is started rising. Okay, and this voltage is called knee voltage. Okay, so this is the forward biasing graph. Okay, then second one is reverse biasing. Okay, reverse biasing is the P region is connected to the negative terminal and N region is connected to the positive terminal. Okay, then when we draw the graph, okay, then it will be in the third quadrant. Okay, so this is the current I and this is the voltage. Okay, here the current is measured in microampere. Okay, then initially there is no current up to a certain value, and after that there is a small rise in current. Okay, so and this voltage is called breakdown voltage. Okay, clear? So this is the graphical representation of reverse biasing. Okay, now, okay, so this is the end of this question paper, sample question paper discussion. Okay, I hope all of you understood the discussed 35 questions. Okay, so all the best for your upcoming exams. Thank you.